Will start sharing my screen here.
Yes, welcome everybody. So this is Byungchul Cha from Muhlenberg College, talking about intrinsic Diophantine approximation on circles.
All right, thank you very much. Thank you for the organizers for having me speak here today. It's a great pleasure to give a talk here in the seminar on the topic of intrinsic Diophantine approximation of circles. So everything I will say today is a joint work. A large part of this, oh, let me go to the next slide here. A large part of what I will say will come from the first paper that I posted with Tohan Kim. That's in arXiv, intrinsic Diophantine approximation of a circle and its Lagrange spectrum. Some of them will come from another paper of mine with my undergraduate collaborators, which is also up in arXiv. And then later in the talk, I will discuss our ongoing. I'll give you a progress report on the ongoing work on Diophantine approximation of spheres, two-dimensional spheres. So that's that paper has not been completed yet, so it's coming hopefully soon. Right. So I'm going to start with a very elementary, maybe overview of some definitions. So I'll start with the definition of Lagrange number, which I gave over here. So basically, the Lagrange number. So in literature, there is a definition of this type, or some in other literature you can define it as its reciprocal. But basically, the definition I will use here, is that I will multiply the distance with the height factor, and then take a lim suit of that. Well, I take the reciprocal of that, and then I take the lim suit. So this is a familiar definition, which it took a long time for me to sort of wrap my head around this concept of Lagrange numbers. And so maybe I'll just try to give you a very silly way of understanding Lagrange numbers, just because this was a very difficult concept for me in the beginning. So, as you all know, Diophantine approximation is about approximating real numbers using rationals. And here's how I kind of envision the concept of Lagrange number here. So imagine there's a real line, and then you place a light bulb on every single rational numbers, but not on irrational numbers. And then your light bulbs comes with different brightness, so to speak. So at a point, say P over Q, the brightness is determined by 1 over Q squared. So the light goes only up to this far. But if you take a fraction with larger denominator, then the light is a little, less bright. So it goes only about that. And then you ask yourself, now we're going to let the capital L to be 1 for now. I'll make a silly definition here. So each irrational number, C, we're going to say the irrational number is visible if the irrational number receives light from infinitely many nearby rational numbers. Okay, so of course that would mean C minus P over Q is less than 1 over Q squared for infinitely many rationals. And this should remind you of the famous theorem of Dirichlet, which, by the way, may or may not be due to Dirichlet himself historically. I don't know that very well. And anyway, so what that theorem says is that every irrational number is visible, because every irrational number gets light from infinitely many light sources nearby. So that's my idea of, and that's what the Dirichlet theorem says.
But visibility depends on this L, right?
Correct. Now, that's the story when L is equal to 1. Now what you will do is you will dial up L a little bigger, which means that every light bulb on the irrational numbers will uniformly darker and darker and darker. You let your L get bigger and bigger and bigger. And at some point, some irrational numbers will turn dark. They won't be visible anymore. And when that happens, and the fact is that the worst approximable number will turn dark fast, and that number L is actually going to be, according to our definition, is the Lagrange number of that irrational number. Okay, so that's sort of the way how I'm thinking about this. So okay, so the usual definition here is that you collect all the Lagrange numbers for every irrationals, then that's the set of all the Lagrange numbers are going to be called the Lagrange spectrum. Like I said, the golden ratio, we all know, is the worst approximable numbers, and that's the first number that turns dark, is as your capital L increases. And then after a while, square root 2 or its equivalent numbers will turn dark as well, and that happens when L is equal to 2 root 2 and so forth. And I'm going to make another maybe silly definition here. We're going to say that a irrational number C is very badly approximable if its Lagrange number is less than the smallest accumulation point of the Lagrange spectrum. In other words, if Lagrange number of C exceeds only finitely many numbers in the spectrum. Oops.
Is it 3? What is the smallest?
In the case of real spectrum of reals, it is 3.
Okay.
But if you change the Diophantine space, that number can change, obviously, right? So, but this definition should still make sense. Very badly approximable if its Lagrange number exceeds only finitely many other Lagrange numbers. So that's my definition. Now, the more common definition of badly approximable numbers would be, of course, when Lagrange number is less than infinity. And we insist for it to be very badly approximable, it has to be really bad. Lagrange number has to be really small so that it belongs to this discrete part of the Lagrange spectrum. Now, this is the regime of the Lagrange spectrum that we're going to be interested in this talk. Okay, so that is my, so before I move on to the general formulation, the famous theorem of Markoff, coming from 19th century, is characterizing the entire discrete part of the Lagrange spectrum of the real line. And they are given by this amazingly simple formula, square root of 9 minus 4 over m squared, where m is so-called a Markoff number. And Markoff number is an integer solution to this equation, which is historically referred as Markoff equations. So the very badly approximable numbers, C, characterized by Markoff, can be explicitly described by the continued fraction. So, so this is all well-known results from Markoff. So they have a very specific and concrete characterizations of the repeating part of the period of in the continued fraction expansion. So that's all Markoff, and that's all well-known part. Okay. So now I want to move on to the more general setting. So I will be interested in intrinsic Diophantine approximation, meaning that our space comes with a metric. It's a complete metric space, and the approximating rationals will always be a subset of the ambient space X. And it's countable dense so that I can approximate any point in X. And then I will equip the dense subset Z with a height function, which is the usual business for us to do. And then I will define my Lagrange number just the same way, the reciprocal of height times the distance between P and Z. And then we're going to take, of course, the lim sup as your height of the rational object, Z, goes to infinity. So if you're an expert in this area, then you'll probably have already noticed that I do not bring in the concept of a Dirichlet function in formulating the Lagrange numbers here. That's just for the simplicity. So for those experts, what I will do is I will simply fix a optimal Dirichlet function so that we have plenty supply of badly approximable points, and then we will sort of subsume that Dirichlet function into the height. So basically, height function already contains the Dirichlet function. And we will denote the spectrum as before, the calligraphic L. And then the Lagrange numbers of very badly approximable numbers will be, calligraphic L with subscript B for very badly approximable numbers. Okay. All right, so that's the notations that we are going to do here. So maybe I'm not very well aware of all the existing literature, so I will probably do a bad job, conveying all the literature review here. I will say just one thing for this talk, which is intrinsic Diophantine approximation done by Dmitry and Keith Muriel and their collaborators. So there's a couple of papers that I'm aware of. These are Journal of Math and Transactions in AMS, where they prove that for Sn, for n sphere, and more generally, non-degenerate submanifold of Rn, they are able to show that the set of all badly approximable numbers is a full Hausdorff dimension.
Excuse me, Byungchul, can you stop for a second? Because there is a question in chat from Samantha, and probably, Samantha, if you can ask, maybe it's better if you just do it
yeah.
yourself.
So I think maybe it was for like the experts that you were talking about, the Dirichlet function.
Yeah.
But on the previous slide, I'm just checking. Basically, what you're saying is this height function, like there exists. Are you saying that there exists this height function so that this lim sup information is well defined, and you can always find a height function for any discrete subset in the metric space that you're using for your Z?
So I think what I was saying is usually the way we define the Lagrange number is Dirichlet function. If I call this the Dirichlet function like phi, then usually the way it is defined is phi of height Z. And then you multiply that with the distance.
Okay, and you're just incorporating that into the height function.
Exactly.
Okay.
Yes. So for example, so in the case of rational numbers on the real line, the height was just q, right? Or q squared. I forgot what was it.
Right. So if I go back to this slide,
yes, q
the
squared.
more normal thing to do is height is q, not q squared.
But here you have q squared.
But I have q squared. That's because the optimal Dirichlet function is something squared. So what I will call is, I will cheat a little bit and I'll say just height is q squared.
Exactly. So because if you instead put q cubed, it will not be an interesting.
Right. Then I won't have many badly approximable numbers.
Yes.
And so you're saying you're choosing the height function so that this is an interesting problem then?
Exactly. I fix an optimal height. I fix an optimal Dirichlet function. And then my height is, in fact, height composed with the Dirichlet function.
Okay. Thank you.
All right. I hope that makes sense. All right. Okay. Well, I don't know how I set my Zoom setting, but I'm some reason not able to read the chat. So if you could, Dmitry, interrupt.
Yeah, that's fine. Yes. I can take care of this.
Yes. Thank you. But yeah, please feel free to interrupt at any time.
By the way, if anybody has any questions, you can just write in chat. or ask directly, whatever.
Yeah. Okay, so that's where I was, and so yeah, that was actually a good comment because I think it's due to the work of Kleinbach, Merrill, and other papers that the Dirichlet function here is 1 over whatever the quantity, and then height is q. So when you compose them in our setting, it's just height is the common denominator of a fraction if you're interested in n sphere. Okay, so that's how we fix the height so that we have plenty of supply of badly approximable numbers. And this will serve at least us well for this talk because I am mostly interested in spheres. So this choice of height will work for the rest of the materials in the talk. Okay, so here's my first results. So we were able to characterize all very badly approximable points in one sphere, that's a circle, sitting inside of R2 with the usual rational points. Maybe a historical remark was after we posted our paper in archive, it was Nikolai Mushevichin who kindly let us know that there's this paper of Kopetsky, came out in 1985, which in probably a little less direct way essentially proved similar results as ours. So that's why I put both names up here. Certainly Kopetsky's proof relies on different kind of method. And our method is probably a little more direct than Kopetsky. At any rate, the statement goes like this. It's very similar to Markoff's original statement. What it says is that all the Lagrange numbers of very badly approximable points are characterized this way, coming from slightly different Markov equation, 2x squared plus y1 squared plus y2 squared equals 4xy. And then they give Lagrange numbers with respect to this formula, depending on if you're x or y, okay? So that's that. And what's missing in this statement, but what we are able to also prove is that we're able to use something related to something similar to continued fraction. So we're able to characterize all the very badly approximable points, and we're able to give their coordinates precisely. Okay, so that's going to be that is our theorem. So the proof of this theorem is going to be essentially the starting point of the proof will be the construction of digit expansions for points on the unit circle here. Okay, because then we're able to follow what Markoff has done and be able to characterize very badly approximable numbers. Okay, so so next slide is I'm going to spend a few slides in order to describe how we're.
I had a quick question. Sorry, I had a quick question on the previous slide.
Yes.
Yeah, go ahead.
So okay, so you've got infinitely many of these, and you're saying this is. I'm trying to connect this with the very nice picture you had with the, the various results on the reals, right? So this is
this thing.
Yeah. So my question is there a Hall's ray in your S1 setting?
I believe so. I strongly believe so, but I haven't written down the proof. We had some discussions with Tonghan, and we strongly believe that.
And you also think you can pin down the analog of the prime and constant?
That should be harder. I've never tried, but we didn't try. But there should be a Feynman's constant.
Awesome, thank you.
Okay, but can I maybe build up on this question? So if you so you can talk about rational points on the circle, and then you can talk about rational points on the real line, and then you can set up a stereographic projection from a circle to the line.
Yes.
And then rational points will be in one-to-one correspondence.
Correct.
But the constants will change a little bit.
The height will change.
The heights will change. But is it true that the heights will only change by the bounded amount?
Yes, that is true.
So then it follows, from this it follows that holes ray exist already, right? Because but you don't know which one, but, I mean, where is the starting point, but somewhere it should start. So it's just the proof that the proof of the existence of the holes ray, I think it's not a big deal.
Right.
My understanding.
Yeah, that's actually what I was a little, so I'm going to connect it with maybe Sam's question from before. So the stereographic projection that you just mentioned, does that sort of, match the change in the height? Because, previously we had, I think height was q squared on the reals. And then in this slide, height is q, right? So is that designed to match this stereographic projection?
Well,
I'm asking it in a stupid way, I'm sorry.
No. This is actually right in the point. And maybe I should even mention that the exact amount by which how the height is behaving on the stereographic projection is actually the starting point of Kopetsky's method.
Ah, okay.
So Kopetsky is kind of using, his language is a little difficult to track, but I think as far as I understand, Kopetsky's method was to characterize that height, characterize the change of the height under the stereographic projection. And what he discovers is that, well, basically height changes only two ways. Either it preserves the height or the height reduces exactly by half. Mm-hmm. The cancellation is exactly by half. So what Kopetsky discovers is, well, then the spectrum is not going to be exactly the same as the usual real line with rational numbers, but you have to kind of weigh the rational numbers differently in terms of the parities of numerator and denominator. And that work has already actually been done a few years earlier by Asmus Schmidt in the 70s. I'm probably getting ahead of myself a little bit because this is going to be a key point in my later part of my presentation. So, yeah. I hope that makes sense for now.
Yes, please keep going.
Yes. So this is very important observation. So, and then we are trying to capitalize, precisely on that point later on when we discuss the spheres. All right. So anyway, so that's where we are now. So what I'm going to do now is that I will basically convince you that our proof of this statement is going to follow very closely the classical proof of Markoff, in that we're going to define continued fraction-like digit expansion on the unit circle, and then we will just follow what classically, how this theorem is proved classically. So the first thing is to define a digit expansion for points on the unit circle. And then the starting point for that for us is to recall maybe a little less known theorem on Pythagorean triple called what I call Berggrun's theorem, which says basically this: every primitive Pythagorean triple is in the orbit of 101 or 011 via the action of the semigroup generated by M1, M23. These are the three matrices. That's a pretty old theorem, and we're able to, and then you can use this theorem to generate the digit expansion. So one way to explain this theorem, like graphically, is to show you this tree. You start out 101 and then 011, and then you keep multiplying these matrices M1, M23. Then Berggrun's theorem says, there you go. That's how you get every primitive Pythagorean theorem in a unique way. So using that theorem, what we're able to do is that we can use, actually this is done by Dan Romick in this paper 2008. We're able to define a digit sequence for every rational point on the unit circle just by following or tracking your triple in the tree and then call them D1 through DK, where every D is either 1, 2, or 3. And this is exactly how classical continuous fraction can be described if you think of any rational number as an orbit starting from 0, 1, and then you multiply these matrices, okay? So, and then you can, use this digit expansion to approximate irrational points on the unit circle as well. This can be written in a more straightforward way by writing down the Gauss map-like map T. So my T is very similar to Gauss map, but it goes from a quarter circle to a quarter circle defined by these this expression. Now, this expression obviously comes from the matrices M1, M2, M3. And then you define your digits, D1, D2, D3 this way, and then you iterate your map T, and that's how you define your digit sequence, okay? So this is all done by Romick. And so my talk is going to be mostly number theoretic stuff, but I will try to throw in a little bit of dynamics here for other people.
Wait, so continued fraction now has only 3 values, 1, 2,
correct. And 3? Exactly right. So our digit expansion is sort of a slowed down version of continuous fraction map. It has only 3 digits.
Okay.
Yes, that's exactly right. So this is, if you conjugate the quarter circle into a unit interval, then this is what the graph of the map T looks like, okay? So remember, if you, the usual Gauss map graph has like infinitely many branches, which allows us to have infinitely many digits, but right now we have only 3 digits. So that's why we have 3 different inverse branches. This map has been introduced before by Aronson and Denker going way back 1999. And what they did is actually to realize this map T hat as a factor of a section map for a geodesic flow on F bar. What is F? Well, F is the fundamental domain of a surface, upper half plane modulo gamma 2. And then if I throw in a little more dynamics here, more recently Panty was able to construct a hyperbolic billiard table in the Poincare model, encompassing this example and a more general billiard table consisting of a unitary system, what he calls a unitary systems. So that has been published very recently. Anyway, so coming back to our proof, the main essence of the proof is that after we define what it means to have a digit expansion on each point on the rational, on the point in the unit circle, we prove a version of Perron's formula, which looks like this. Now this expression is obviously 1 over height times the distance, which is how we define the Lagrange numbers. And then after you have this version of Perron's formula, we are able to proceed just like Markoff did, which means using this, now we're getting into a combinatorics region. That is, we are able to produce a few examples of quote unquote forbidden sequences if your number if your point P is very badly approximable. Now, of course, I have to say that a priori, you have to have a guess for the smallest accumulation point in order to define the forbidden number, but that's easy to do. And then after you find enough forbidden digit sequences, your combinatorics will tell you exactly what kind of combinatorical patterns there are left for a very badly approximable points have. And that should give you the final step of the proof. So that's the very broad overview of our proof. Okay, so now before I introduce my next results on the Diophantine approximation of circles, I'm gonna maybe give you even more silly definitions here. I'm gonna define Diophantine isometry which is really simple. If you think about it, if you want to do a Diophantine approximation, you will want to have an isometry, but not only an isometry, you want to preserve the rational object in the two Diophantine spaces, but also you want to preserve the height. So that's what I mean by Diophantine isometry. Maybe it's a little stronger than what I really need, but let's just make this definition for now. Obviously, this kind of isometry will preserve Lagrange numbers, so that's trivial.
Then probably you can also have a notion of Diophantine quasi-isometry.
Which means this is preserved in the limit.
Up to some constants or something like this.
Right, yes. You can relax it a little bit by allowing some positive constant uniformly, but also you can do, you want it to be an isometry only locally, because the notion of Lagrange numbers is just local.
Okay, sorry.
Okay, so this was the what we mentioned before. If you now give yourself, if you regard the unit circle as a unit circle in the complex plane, then our rational object, the rational points in R2 will simply become points defined over Q of square root of -1. And then this is a little number theory exercise here, that the height of A over C, comma B over C, which how we fixed our height for all the spheres, is actually matching the height in S1 case, in the case of complex numbers, where we define height to be the square of the bottom, B times B conjugate. Then it is a number theory exercise that these two heights actually match if you define your map in the most obvious way. Then this is Diophantine isometry. So, you can get this theorem for free. We just had a theorem regarding S1R2, comma S1Q2. Now the same theorem will say S1C, comma S1Q of I will be just exactly the same thing. So that's just a trivial observation. The reason why I want to bring this in is because I wanted to do this with now this circle. Well, this can be a circle depending on what metric you use. So if you now define a rational object in the unit circle in the complex plane differently, namely you declare your complex points rational when the point is defined over omega, which omega is a sixth root of unity. And then, but then height is defined the exact same way. It's the norm of the bottom. Oops. Then what you can show, again, using the same number theoretic exercise, you can show that these two spaces are Diophantine isometry, under Diophantine isometry, in the most obvious way, x plus omega y getting mapped to x comma y. But then now your distance in R2 is not defined by the usual standard distance, but now this is a distance function on R2 given by the inner product, which should mimic the behavior, of the Eisenstein field. So therefore, we know that the Diophantine approximation on this space is the exact same thing as Diophantine approximation of the second space. Why do I care? Because I know something about the second space, because there is a theorem about these Eisenstein triples, very much like Bergeron's theorem for Pythagorean triples. So the theorem there is exactly identical, exactly the same, namely that if you give yourself now these 5 matrices, then every Eisenstein triple, which of course I mean a squared plus ab plus b squared equals c squared, is in the orbit of 101 and 011 via the action of these 5 matrices, semi-group action. So again, the picture description of this theorem is, you just draw the same Eisenstein triples starting with 101 and 011, and this picture I think should be enough to convince you that there's a exact same process of creating a Ramek map, and then you can create a create a digit expansion on points in that quote unquote circle. And using that, you go through the combinatorics, and then you again find enough forbidden digits. And finally, we're left with these very badly approximable points. So the theorem now we're able to prove using that combinatorics is that the very badly approximable numbers are now characterized by these numbers. But then you see this, it has much less complicated structure than the classical case because there's no Markoff-like equations. You know, Markoff numbers grow in a pretty mysterious way, and we are not sure how fast Markoff numbers are growing, but these numbers, everything is completely written down explicitly. Okay, so these are just two quadratic, numbers defined exactly like this. So we have a very precise description. This is just saying that the combinatorics regarding the two spaces are different, and this Lagrange numbers are coming out differently. Okay, so we're able to prove that this is the spectrum for this space because this holds for both, and both spaces are under Diophantine isometry. Okay, so that's that. We can do more because there are more trees like this, not only for Pythagorean triples and Eisenstein triples, but in a paper that I wrote with my undergraduate collaborators has a few more trees like this. So here's an example, 2a squared plus b squared equals c squared. And they are looking a little bit more differently, but still we're able to carry out basically the same business. We're able to create the digit sequence for the corresponding quote unquote circle. And then we're able to prove, in this case, the Diophantine isometry we're constructing is looking this way. So this is quote unquote my circle, but then that is matched up with, again, a complex unit circle now whose rational points are characterized by, points coming from the rational, coming from the imaginary quadratic field Q of square root of -2. So again, this then gives you a complete description of very badly approximable points in the complex unit circle. Okay, so when we carry out all this analysis, we found out that the spectrum turns out to be exactly the same. And well, using Dimitri's words, it's quasi same because I have an extra factor √2 in front here. But we're able to prove that this is the spectrum for the complex unit circle in the case of Q of square root of -2. So to summarize, what we're able to do is using this new kind of digit expansions, using those trees, we're able to find intrinsic the Lagrange spectrum very badly approximable part for complex unit circle, where we have 3 different rational points. First case is Q of I, the second case is Q of omega, the usual omega, and then the third case is Q of square root of -2. In these cases, we're able to describe all very badly approximable numbers. All right, so that's our results on S1. Now I want to move to S2. So this is what we're still working on. So we haven't released our preprint yet, so we're still working on this paper. So before we get into this, let me give you a very brief overview of all the results of Asmus Schmidt coming from 70. So he wrote this paper in ActaMaths 1975. So he developed his theory of C regular chains, and his main business was to do Diophantine approximation of C by imaginary quadratic fields, different imaginary quadratic fields. So I wrote that he was able to describe all very badly approximable Lagrange numbers for 1, 2, 3, 4 different imaginary quadratic fields. So Q of I case already appears in the main paper. And then he's able to do different combinatorics and then able to deduce all very badly approximable numbers for 3 different imaginary quadratic fields. So as an example, the first case Q of I, so his theorem says that the very badly approximable Lagrange numbers are basically given by half of what we had before. There's no letter y. We only have x in here, the square root of 4 minus 1 of x squared. And then he has to add this exceptional Lagrange number coming from this root of this quadratic equations over Q of I. So this is a very important work in 1975. Now, what we're able to do with this is that we are able to use this results of Schmidt, and then we're able to connect this with the very badly approximable, or in general, Lagrange spectrum of S2, given by the equation x squared plus y squared plus z squared is equal to 1. And then what we found is that the spectrum is precisely the same as the complex spectrum found by Schmidt. You just need to throw in 1 over root 2. So this is the complete spectrum of S squared. I mean S2, the usual 2-sphere. Now, the proof, the main idea of the proof has already been discussed earlier in this talk, because we already talked about how the stereographic projections change the height. So I have to expand a little bit on that point. So that's going to be our main idea. It's going to be much simpler than what we had in the case of S1. So here's how it goes. The stereographic projection, let's do the usual stereographic projection from 0, 0, 1. Going down to, x plus iy divided by 1 minus z, the usual stereographic projection. And I'm going to call its inverse sigma, okay? Now, then what we have is, if we have a rational point in the complex plane close to Xi, then what we want to do is we want to compute them using sigma, and we hope that they're matching. So if you use the Jacobian factor and then you calculate the distance in the sphere using the Jacobian factor, and then you kind of, change your expressions a little bit, what you have is this. At the end of the day, you have height of the complex plane times the distance in the complex plane. And what you have is this expression, height of the point on the sphere divided by norm of alpha squared plus norm of beta squared divided by 2. And you hope that these two things are the same. If it were the same, then we will show that these two spectrums would be exactly the same, right? But they're not the same. And the behavior that we're able to see, which was not difficult at all, is that in fact it changes by a factor of 2, depending on alpha and beta are the same modulo 1 plus I or not the same modulo 1 plus I. So because this height and this expression right there is different by a factor of 2 only in half of the time, what we need to do then to make this argument go through, we need to change, we need to fix the height. So here's what we're doing. What we're doing is we're mapping C to itself by this map right here. This is, geometrically speaking, simply just a rotation centered at complex number I by negative pi over 2. Now, if you just do the rotation 45 degrees, then that's not going to send all the rational points to rational points. So what you need to do is, after you rotate it, you have to do some dilation. Now, we did the dilation by 1 over root 2. After that, then every rational point will go to another rational point. And it does what we want to do. It changes under this map phi. It changes the height 1 or twice, exactly half of the time we want it to be corrected, the way we want it to be corrected. So to recap, what we were able to do is when we're hoping that this is equal to 1, in fact, this is not equal, this part, red part is not equal to 1, but this part times the complex height is actually equal to the complex height of the number alpha prime over beta, alpha prime over beta prime, which is alpha prime and beta prime is the image of alpha over beta under the map phi. So you write that down instead, and then of course the map phi changes the distance by a factor of 2 very obviously. So after you finish everything, you have extra factor root 2 up there, which will be 1 over root 2 because the Lagrange number is reciprocal of height times distance. So that's how we're able to prove that the two Lagrange numbers are exactly the same. Now, maybe this would be a good point to go back and recall the work of Kopetsky, because for the Kopetsky's case, in the real line, the kind of map that we have, like phi is not available. I mean, there's no rotation for real lines, so we have less room kind of to move around the real line. So we're not able to come up with a map phi like that. Therefore, Kopetsky had to rely on a different work of Schmidt to deduce the spectrum. But in some sense, for complex plane, we have more kind of freedom to work around. So we're able to find the map phi and able to prove that the two Lagrange numbers are exactly the same. Okay, so that's very geometric and intuitive proof how or why the spectrum of the two spaces are in fact the same. The summary, therefore, is this. So you start with S2, and then you do the usual stereographic projection, and then you find yourself that your height has been behaving badly under the stereographic projection. So you need to introduce another map phi, which is usually a rigid motion followed by dilation to fix the changes in the height. And then after you compose those two things, then you're able to match up the Lagrange numbers between the two spaces. So that's what we're able to do. Okay, so that's that. And now let's recall the work of Asmus Schmidt, which is actually not terribly old. So he also was able to prove a complex spectrum with the rational points being q of square root of -2. Now this is already, the very badly approximable part is very different from before. We have only 3 points in the discrete part, and then the smallest limit point looks pretty horrible. So that's the case for a complex Lagrange spectrum, and we're able to show that a different sphere defined by this equation, x squared plus y squared plus z squared is equal to 2, and rational points is the usual rational points on this given by this embedding in R3. Then, in this case, the Lagrange spectrum of the Lagrange spectra of the two spaces are exactly the same. So we have a complete description that's coming from Asmus Schmidt's prior results. And the proof of the theorem is actually the same. So all I need to do is to tell you what kind of stereographic projection we're using and how to fix the height problem using the phi map here. So this is how we do this. The stereographic projection, we choose the base point to be 0 and 1, and then we project it onto this plane, y plus z is equal to 1, sitting on R3 using this formula. And then you compose that with phi, which is actually, again, a rigid motion followed by a little bit of dilation. And then you're able to prove exactly the height matches the way we want it to match. And then we're able to prove that those two spectra are exactly the same thing. One more. So here's the theorem of going back to Schmidt again, 1983. Now, the discrete part has infinitely many points, but then again, the combinatorics is different. So we have pretty scary looking numbers. And then the first limit point is this number, and that's from 1983. And we are also able to find a sphere we call S2 subscript 3. Now this sphere is embedded in R4. How is this sphere embedded? These are the defining equations. So we're in S4. You define S2, two sphere by intersection of these two hypersurfaces, x1 plus y2 plus x3 plus x4 is equal to 1. And then product of these things, sum of those things is equal to 0. Now this is the sphere, if you trust me, centered at this point, 1/4, 1/2, 1/4, 1/4, 1/4, 1/4. The reason why I need to specify this coordinate is then this is telling me how the rational points are defined, how the distance is defined, so that we have everything well defined. And then we're able to prove that this spectrum is equal to the Schmidt spectrum divided by 1/2. Okay. Again, the proof is the same. I need to tell you what is the stereographic projection. And in this case, we projected onto the plane x plus y plus z is equal to 1 onto R3 using this formula. And then after that, this is again a rigid motion followed by a little bit of a dilation or shrinkage, whatever you want to call it. But then this is the kind of a slant plane in R3, but then you project it into a pretty symmetric way so that 1, 0, 0 goes to 1 and 0, 1, 0 goes to the usual third root of unity, omega, and then 0, 0, 1 goes to its conjugate. And then you can proceed and do some unpleasant calculations and you prove that heights match exactly the way we want it. So we're able to prove that these two things are the same. And so just a summary, we found that very badly approximable numbers on these three different spheres whose rational points are all differently defined because we embedded the sphere in different ways. But then those spheres are defined so that they match the Lagrange spectrum of Asmus-Schmidt, where you change your imaginary quadratic fields into these three different ways. And then we rely on the results of Schmidt, and then we will then be able to find the very badly approximable numbers in those three spaces. Okay, so that's all I have. And thank you very much for listening.
Okay, thank you, Byungchul. So let's give a round of applause, either virtual or with real sound. Something like this. So any questions? We still have time to official time.
I just want to ask a few questions. So is it true that you considered several types of two-dimensional spheres and you were able to calculate a discrete part of corresponding Lagrange spectrum by reducing to these results by Asmus-Schmidt?
Right.
So for these spheres, you know the beginning of spectra.
Yeah, that's right. I mean, the reason why we have to rely on Schmidt is that we never did the combinatorics in S2 case in order to characterize the very badly approximable part of the spectrum. So what we did is simply we described how stereographic projections change the spectrum of S2 and how is that related to the spectrum of C, basically.
Okay. So basically the abstraction for doing it for three-dimensional sphere is that there are no complex numbers and no Asmus-Schmidt who did this before.
That would be the limitation if I want to push this to S3.
I see. As far as I remember, Asmus-Schmidt had description for not for too many Fuchsian groups, but for several. I mean, complete description with discrete part.
Correct. So the only thing I think we're missing here in this list, I hope you're still able to see my screen. Are you?
Yes.
Okay. So as Ms. Schmidt has, I think, one more, q of square root of -7. And Dohan, as we speak, is still looking for a sphere where he can match the different. He's looking for a different sphere whose spectrum would match q of square root of -7. Seems a little difficult, but you know, there are some geometric ideas that go into this, which I haven't described in this talk yet. But yeah.
But how? Where does this list come from again? It's just what Schmidt did, or is it just a finite list of fields for which it's technically possible?
Well, Schmidt was able to do these fields and q of square root of -7. The reason why he's unable to do many more is because the combinatorics is difficult.
Mm-hmm.
So yeah, I'm really glad with these questions, because this slide was where I wanted to ask about. So these imaginary quadratic fields, they're very special. And so I'm repeating Dimitri's question as well about, why is it these lists? And then let's include minus, which one you said, -7?
Yeah, -7, yes.
Right, so they all have class number 1.
Yes.
And there's a finite list of them. And I think Nikolai said something about Fuchsian group, but I think he means Kleinian group, because there's an underlying Bianchi group, right? Because these imaginary quadratic fields correspond to complex lattices, right? So
yes,
if you look at S2 as the boundary of 3-dimensional hyperbolic space,
yes,
then, right, you can look at PSL2 of the
complex integer,
right? O of k, where of the corresponding imaginary quadratic.
Absolutely.
Maybe I just want to get that clear. It's a Kleinian group, right? Whose limit set. I mean, we're looking at approximation of a Kleinian group, not a Fuchsian.
Yes.
So why are there? So there are other class. So I don't know anything about the Schmidt papers. So this is a very naive question. I know you said something about combinatorics, but what exactly do you need? Because one aspect should be, if the domain is Euclidean, right? So if you have a Euclidean algorithm,
yes,
you should still be able to, run the whole approximation mechanism or machine.
yes.
Right? So what are your thoughts on, what has the class number got to do with it? And I'd also like to hear your thoughts about, do you ever think about this in terms of lattices rather than hyperbolic geometry? Because that's the next thing is like the pictures you were drawing were reminding me of norms of these, right? Like the norms associated with the ideals of these.
So for the second part about the lattices, I don't think of it that way. So I have very little to contribute to your question. I will say something about the combinatorics because that's something that I have experience with. So again, going back to this slide, for example, the idea of characterizing every very badly approximable numbers, to me, if say you want to do other complex numbers of say class number 1 that has not been done, for example, then what you need to do is use some sort of a digit expansion, either using Schmidt's C regular forms or whatever Ronick or whatever digit expansion system you're working with. And then you have to have a very good idea of what is your first smallest limit point. And then with that, you turn everything into, like, you basically have to characterize how your shift map is changing your quantity basically given right here. And that is the first clue of like, oh, if it's very badly approximable, then I cannot have the digit expansion of say 1, 1, 1, 1, 1. In the classical case, if you have too many ones, say for example, in the usual Diophantine function, that means your number is too close to a rational point. So that cannot be very badly approximable. And then you have to find a lot of those patterns that are forbidden in order to kind of be able to write down the full list. So that's where the combinatorics gets complicated.
So can I just ask a quick question, because there are too many spheres and I kind of lost. So if you come back to the very basic S2,
yes,
standard S2 inside R3,
yes,
and approximate by rational points on S2. So what is the very worst approximable point?
it is the symmetry point that we know, 1 over root 3.
Root 3. Okay.
It's the symmetry point on the sphere.
And is there any soft argument which would prove this for other spheres? I mean, for other spheres, can you guess what is the worst?
Right. So I did think about that, not from along the line of stereographic projection, but more like our previous idea using the trees of triple or quadruples. S3 is a little difficult because the symmetry points happen to be a rational.
Yes.
So that's a little difficult.
Okay.
If I go up to S4, I mean, I would, if I am forced to guess what it is, then I would still guess it's a symmetry point, but I have very little ground to prove that.
Yes, square root of 5 is a nice number, certainly.
It is
to be not well approximable.
It is. It is related to golden ratios, but moving up to dimension, and then the tree becomes very complicated.
Yeah, this I understand, and I'm just wondering about this symmetry consideration. If it's really the symmetric point. Maybe.
I mean, that's my guess because I don't have any other idea.
Okay. All right. Other questions, comments?
Oh, just a quick one, if I may.
Yeah.
Okay. So going back to the issue of the digit expansions.
Yes.
Can we characterize the Diophantine equations that admit a dynamical kind of solution, like so for which we can construct these Lagrange trees?
I'm sorry, what was the question again? Can we do what?
So can we characterize the equations for which the solutions are described by something like Lagrange tree? So from which we could derive a description with digits like you did here.
Can we get an equation describing the point whose repeating digits are written in some way? Is that your question?
So if you go to your first example of an isometry.
First example of isometry?
Yes. So here. Well, because you had transformed your circle into a different curve. And
Yes.
then you were saying, all right, but then this curve is described by a certain equation, and I can find solutions, so integer solutions to this equation, and from those I get some matrices, and I can use those matrices to create a digit representation of, so a digit expansion of the points on this curve.
You mean this curve? I don't think I'm understanding. I'm really sorry.
Don't worry, it's okay.
Sorry about that.
Yeah. Okay, but let me try to ask a related question. So in this case, back to the standard unit circle in R2, and this trigraphic projection, which right. So I'm still kind of. I mean, maybe it's a naive difficulty, but I still have trouble So technically, I mean, you have a Gauss map on the unit interval, which comes with this infinite partition.
Yes.
And isn't it possible to just use the stereographic projection and somehow conjugate the Gauss map and have the same type of map on the circle, which also will have infinite partition? It's not how it works.
Yeah, no.
Well, for some reason, here you have only 3 intervals.
Yeah, I think again the problem is the same when you.
Because of parity.
Because of the parity, correct. So, because it matters from which point you're stereographic projecting. If you choose this point, for example, as your base of stereographic projection, which is 0, 1, or so if you use this one, then the height consideration will show that. Okay, let's do it this way. 0, 1. We're going to call this an odd point. Actually, let's call this point an odd point. 1, 0 is odd, and 0, 1 is even. And all the orbits of this point we will call odd, and all the orbits of this point we'll call it even. Okay. Now, if you stereographic project based on this point, then it will sort of give extra advantage for all the odd rational points. Whereas if you do it from this point, then under the stereographic projection, you're preferring all the even. And that cannot be erased in R by doing any transformation.
Okay.
Yeah.
Maybe it's a good way to see it. Other questions? We still have some time. And if not, let's give another round of applause to Byungchul.
Thank you.
And it was a great talk, and we hope to see all of you again during the next couple of weeks.
Thank you.
And in the future. Thanks.